So moving forward came relativity. So in the 20th century, this guy in the middle that you know very well, we don't present him again, so that's Albert Einstein. He came and he added more confusion to what we thought we understood. Now, as far as relativity is concerned, many people usually think that Einstein is kind of, I don't know, the holy grail of relativity. But the truth is that Einstein at the time almost got scooped because there were people that were already having ideas similar to what similar to what he had, and they were independently developing this fantastic theory. In particular, I can mention here the guy on the right, that's David Hilbert, and the other one on the left, that's Hermann Minkowski. So yeah, this is really a complex theory, but the core points of general relativity, by the way, there were two relativities. So there was first special relativity, where Einstein talks about motion and simultaneity of events and so on. And then after that, we had general relativity, so which is where he explores really the more broader framework of space and time. So as I was saying, the general idea, the core point of relativity is that events are relative, that speed is relative, that time is relative, so there is no absolute time. And this really revolutionized our understanding of space, time, and gravity. So gravity can be affected. I mean, the flow of time is affected by gravity, and space and time are actually one single entity. So that's the big picture we can get from relativity via these guys. So what can we do with that? So the GPS, I think that's the most common example of application of relativity. So, you know, if you have an object that's located somewhere on Earth, maybe people don't realize it, but it's actually not easy to measure the location of that point with great precision. So suppose you have someone that is somewhere in the other part of the world and you are in another place of the globe, and then you want to know exactly where this object is at a particular time. That's not actually easy. In practice, I think they make use of a set of equations, transformations on circles and 3D space. But to these equations, you need to take into account relativistic effects, which is the fact that as an object moves, I mean, if you have different observers, okay, different objects that move at different rates in a gravitational field, the flow of time is different. So you need to take into account these relativistic effects in order to appropriately measure time, okay, location, time. And that's what we use in the GPS system daily to commute from one place to another. So another important point here is nuclear energy. So this actually came with general relativity. That was in 1915. And it's the famous equation E equals mc squared. Actually, I should have added it somewhere here. Okay, I just forgot. Yeah, so E equals mc squared. We are not here to do a lot of mathematics, but the general idea here is if you have, you know, all matter is made up of atoms, and those atoms have at their core a certain nucleus. So if you play a little bit with the mass of the nucleus, you can get a lot of energy that's produced, and that's the purpose of nuclear energy. So we try to generate energy from atoms, or we try to liberate the energy contained in atoms. So that's also another very important application of relativity.